Hey everybody, welcome to lecture 3 of real analysis. The last time we met, we ended up proving that differentiability implies continuity, a classic theorem of real analysis. So if a function is differentiable, then we know automatically it's continuous. Today we're going to derive some formulas for the derivatives of sine and cosine, as well as the product rule and I guess the power rule also. So that's our agenda. Derivatives of trig functions, power rule, the product rule. I guess that'll be enough for this lecture. Some preliminaries right here. The area of a sector of a unit circle in which the angle is x is given by x over 2. To illustrate, look at this unit circle. Here's the angle x. So this pie-shaped wedge, or this slice of pizza here, is the sector of the circle that corresponds to the angle x. And our claim is that the area of this sector, the area of this slice of the pizza, numerically is given by x over 2, where x is the measure of the angle in radians. And to justify this, I'm going to give an intuitive argument. For all of these examples that I'm going to give, the radius is going to be 1. We're working with the unit circle. So let's look at the simplest case. Here's my angle x. We start at the positive x-axis, and we go a distance of 2 pi, and we wind up back at the positive x-axis. So x, the angle, equals, I beg your pardon, x, the angle, is 2 pi. The sector of the circle that corresponds to this angle, 2 pi, is the entire circle itself. In this case, the sector is the entire circle. So the area of the sector is going to be the area of the circle, and let's see, the area of a circle is pi r squared. But r is 1, it's the unit circle. So the area of the circle, or the area of the sector, is pi. So we have x equals 2 pi. Area of the sector is equal to pi, which is 1/2 which is 1/2 times 2 pi, which is 1/2 x. So x is 2 pi, the area of the sector is 1/2 x. Well, that's just one example. Let's look at another example. Here, the sector is half of a circle. So our angle x is pi. And we have the area of the sector that's going to be the area of the semicircle Well, what's the area of a semicircle? It's 1/2 the area of the entire circle. 1/2 pi r squared. And that's 1/2 pi. Well, let's see. That means that's 1/2 x, because in this case, x is pi. So, x equals pi, area of the sector, equals 1/2 x. So for x equal pi, let me start over. For x equal 2 pi, and for x equal pi, the area of the sector corresponding to x is 1/2 x. We'll look at one more example just to drive home the point completely and thoroughly. We'll look at a quarter of the unit circle. So a quarter of the unit circle, this angle x is going to be, well, let's see, it starts at 0 and goes to pi over 2. So the angle x is pi over 2. The area of the sector is equal to 1/4 the area of the entire circle, and that's equal to 1/4 pi r squared, or 1/4 pi. and that is equal to 1/2 times pi over 2. But pi over 2, that's x. So again, the area of the sector is 1/2 x, where x is the angle corresponding to the sector. So the point for this proof that we're about to do is that given the sector, any sector of a unit circle, the area of that sector is 1/2 x, where x is the angle that corresponds to that sector. You know what? I don't think I'll use delta x here. I think I will just use x. By the way, this is a classic limit. Memorize it. If we don't know this and we're a math major, people will think, what's wrong with this person? But if we do know it, they'll think, okay, this person knows their stuff. So this is a limit that we should know. We may or may not have seen it in Cal 1. If we did see it in Cal 1, it was just something that we saw in passing. So if we don't remember seeing it in Cal 1, no big deal. It wasn't part of the big picture in Cal 1. But we're going to need this to do some proofs. So let's prove it. The limit as x goes to 0 of sine of x over x is 1. And I'll mention that x is in radian measure. Anything that has to do with trig functions and limits and trig functions and calculus, the measures of the angles are always in radians. This measuring of angles in degrees goes back about 4,500 years to the ancient Babylonians. They were pretty good geometers. They were. And essentially, they divided a circle into 360 parts. And it essentially corresponded to the fact that if we look at the horizon all the way around, they essentially partitioned the horizon into 360 parts, 1 part for each day of the year. Why they did that, we won't talk about that. But that was their motivation for choosing 360. And before they became really good geometers and learned that the length of a year was actually 365 and a quarter days, They thought the length of a year was 360 days. So essentially, they took the circle which corresponds to the horizon of the Earth, and they partitioned that into 360 pieces. They didn't know calculus back then. If they had, they would have chosen radian measure. Anyway, when we do calculus and limits and trig functions, we always work in radian measure. Now, here is our proof. And our proof has to do with this unit circle. Oh, crud. A for area. The area of triangle OAB is less than or equal to the area of sector OAC and that's less than or equal to the area of triangle ODC. Okay, area of triangle OAB. It's going to be 1/2 the base times the height. And OB is the base, and AB is the height. Well, let's think about this now. What are the coordinates of this point right here? This is a unit circle, isn't it? So this point is on the circumference of a unit circle. And the x coordinate of this point is going to be cosine of x. The y coordinate of that point is going to be the sine of x. So this distance right here, cosine of x, and this distance from A to B, sine of x. Oh, son of a gun, we got the base and the height. 1/2 cosine of x, sine of x. That's the area of triangle OAB. Now, what about the area of sector OAC? Well, based on that result that we had just a couple of minutes ago, in a unit circle, the area of a sector numerically is equal to 1/2 the measure of the angle corresponding to that, 1/2 x. Oh, wow, this is great. And now the last triangle, ODC, what the heck is that area? Well, I'll tell you what. I'm going to claim that it's 1/2 x, 1/2 the tangent of x. Now I have to justify that, don't I? I have to justify that, and I will. And my justification is this. Triangle OAB and triangle ODC are similar. And let's see, why would that be the case? Well, let's see. Both of them have common angle x, and both of them have a right angle. So the remaining angles have to be of the same measure. Triangle OAB and triangle ODC and what that means, among other things, is that the ratios of the corresponding sides are the same. So, in other words, if I take the ratio of side OA and OB, in the smaller triangle OAB, if I take the ratio of the hypotenuse OA and the horizontal leg OB, that has to be the same as the ratio of the hypotenuse of triangle ODC and the horizontal leg of ODC. So the hypotenuse is OD, and the horizontal leg is OC. And you know what? I don't want to do this. Oh, forgive me, please. Oh, please forgive me. I do want to do similar triangles, and I do want to use those two triangles, but I don't want to use the hypotenuse. What I want to use is the vertical leg and the horizontal leg. Triangle OAB. The vertical leg is AB. The horizontal leg is OB. And now I'll do the same thing with triangle ODC. The vertical leg of triangle ODC is side DC. The horizontal leg is OC. Okay, now this is looking like something. AB, that's sine of x. OB is cosine of x. Now, DC, I don't know what that is. But that's okay, we'll find out. OC, it goes from the origin to the circumference of the circle. So OC is the radius, which is 1. This is a unit circle. And I'm going to have to continue this up above because of lack of board space. Sine x over cosine of x. What is that? It's tangent x. And DC over 1 is DC. So the area of triangle ODC is equal to 1/2 the base times the height Here's the base of triangle ODC. Well, the base just goes from the origin to the circumference of the circle, so the base is 1. And the height, this is the length of side DC, which is tangent x. So area of triangle ODC is 1/2 tangent x. That's what I was supposed to justify. Take a look at that for a couple of seconds before I erase it, and then I will get back to our proof. Okay, get back to our proof. This is where we were. One half cosine x sine x less than or equal to 1/2 x less than or equal to 1/2 tangent of x. That's where we were. Now, I think what I want to do is divide by the 1/2 first of all. So I'll just have cosine of x sine of x less than or equal to x less than or equal to tangent x. And then I think what I want to do is divide both sides by sine of x. So I'll have cosine of x less than or equal to x over sine of x. And let's see, tangent x is sine x over cosine of x. So if I divide this by sine of x, I'll just have 1 over cosine of x. I could just take the limits right now, but let's see. If I multiply both sides by cosine of x, and then I multiply both sides by sine of x over x, we get that. And I don't have to worry about the inequality being reversed. We're in the first quadrant. X, sine of x, cosine of x, they're all positive. Now, what about that part? If I divide both of these, if I divide both sides by cosine, then I'll get cosine on the bottom here. And if I multiply both sides by sine of x over x, I'll get sine of x over x. And this will just be 1 over cosine of x. Okay, and again, I don't have to worry about the inequalities being reversed. Sine, cosine, and x are all positive. So here's what I get. I get sine of x over x. And sine of x over x is greater than or equal to cosine of x. And it's also less than or equal to 1 over cosine of x. And because we had this thing called the sandwich theorem a lecture or two ago, I can compute the limit of all three sides of this inequality as x goes to 0. Is that showing up? Cosine of x? Yeah, okay. Good. I just took the limit of all three sides as x goes to 0. Well, as x goes to 0, cosine of x goes to 1. That was one of the limits that we learned from last time. And so, again, cosine of x goes to 0. That's 1. Oh my goodness. The limit that we want is sandwiched in between 1 and 1. Whoops. Voila. Take a look at that for a few seconds. And while you look at that, let me get rid of this picture so that from now on we won't have that picture taking up half the blackboard or half the whiteboard. By the way, this is another one of those theorems that we should know, or another one of those limits that we should know. In trigonometry, there are essentially two limits that we should know. As x goes to 0, sine of x over x goes to 1. As x goes to 0, cosine of x minus 1 over x goes to 0. We should know those two limits, and if we do know them, people will be pretty impressed with us. If we don't know them, they may wonder about us. So we should know these limits. I don't know what else to do here. But I see cosine of x minus 1. And I realize that this is one factor of the expression cosine squared of x minus 1. So I get this idea that I'll take this expression and multiply by its conjugate and hope that I get lucky and it actually turns out to be significant. So I'll just multiply by the conjugate, cosine of x plus 1. And let's see, what is that? Limit as x goes to 0 of cosine squared x minus 1 all over x times cosine of x plus 1. This looks familiar, and I just realized why. 1 minus cosine squared x is sine squared. So cosine squared minus 1, that's just negative sine squared of x. Now I'm looking at this, and I realize that I have sine of x in the numerator and x in the denominator. And we just computed the limit as x goes to 0 of sine of x over x. So I'm going to break this up into the product of two things. One factor will be sine of x over x, because I have some familiarity with that. I have the limit of a product up here. I can write that as the product of the two limits down here. And I know this limit. That limit is 1. And this limit, well, sine and cosine are both continuous. And in the immediate vicinity of x equals 0, the denominator's not going to be 0. So I have the limit of the quotient of continuous functions. That's going to be continuous, which means I can just plug in. Or I can say I have the limit of a quotient where the denominator is not going to be 0. And I can compute the limit of the numerator over the limit of the denominator. Either way, I'm going to get 0 over 2. So limit as x goes to 0 of cosine of x minus 1 over x equals 0. That is exactly what we set out to prove. Now, the reason that I had to prove these two theorems or lemmas is that these limits come into play when we compute the derivatives of sines and cosines. So we just got these out of the way so that when we computed the derivatives of sines and cosines, we'd have these limits handy. In calculus, we never saw the proof for this. Here's where we see it. And we use the definition of derivative. Limit as delta x goes to 0 of f evaluated at x plus delta x minus f of x all over delta x. Cool. Now remember the other day in the last lecture when we were doing continuity of sine x and cosine of x? And we had to use these addition formulas for the sine and cosine of angles. We're going to do it again. The sine of the sum of two angles is the sine of the first times the cosine of the second plus the sine of the second times the cosine of the first. And then we have this guy, we can't forget about it. All over delta x. Goodness gracious. I know. Okay. Oh, I know what to do. I know what to do. I'm looking in the numerator. I have three terms. They don't have a common factor. But the first term and the last term do have a common factor, sine of x. So I'm going to take sine of x and factor it out of the first term. So I have cosine of delta x. I'm going to factor sine of x out of the last term. So that leaves me with minus 1. There. I factored sine of x out of the first term and the last term. Now, I also have the second term, which hasn't gone anywhere. It's still there. I can't ignore it. And all of this garbage is over delta x. I think what I want to do now is just break this up into two different expressions. This term over delta x plus this term over delta x. That's what I'm going to do. There, let's just make sure that I did it right. Sine of x times cosine delta x minus 1 over delta x, yep. And sine delta x cosine of x over delta x Yes, beautiful, beautiful. Okay, I can actually see how this is going to turn out now. I'm seeing it all. I have the limit of the sum of two functions. I can turn that into the sum of the individual limits. Okay, I've got the sum of two limits, and each of these individual limits is a product. I'm going to factor out sine of x here. And you know what? With respect to delta x, sine of x is a constant. So with respect to delta x, I have a constant times this other junk. I can bring the constant out front. Remember, the limit of a constant times a function is the constant times the limit. And this is what we got left. Looks good. I have something similar here. With respect to delta x, cosine of x is a constant. So what I have is the limit of a constant times this function. I'm going to bring the constant out front and make that the constant cosine of x times the limit of the function. Oh, and now I realize what we got. From the previous theorem, limit of delta x is, the limit is delta x goes to 0 of cosine of delta x minus 1 over delta x. That's equal to 0. That's the limit that we just proved. And this limit is delta x goes to 0 of sine of delta x over delta x. That's equal to 1. So here's what we got. By the way, do me a favor and just make these equal signs. I have sine of x times 0 plus cosine of x times 1. And that's just going to be cosine of x. Congratulations, ladies and gentlemen. We've just computed the derivative of sine of x. Ah. Okay, derivative of cosine of x. We're going to do this exactly the same way that we did the derivative of the sine of x, including using addition formulas for the cosine of the sum of two angles. By definition of derivative, we're going to have the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Okay, cosine of the sum of two angles. That's going to be the cosine of the first times the cosine of the second. Minus, if this is a plus, we're going to have minus down here with the cosine formula. Minus the sine of the first times the sine of the second. And let's not forget this term, minus cosine of x all over delta x. And the thing that I did with the proof of the derivative of sine of x, I'm going to do with the derivative of cosine of x. I look in these three terms in the numerator for a common factor, and there is none. But the first term and the third term do have a common factor of cosine of x. So I am going to factor that out. I'm going to factor cosine of x from the first term and the last term. Whoops. So I'll get minus 1. And minus sine x sine delta x. Now, what did I do before? I think I looked at this thing and I said I have the limit of one expression. I'm going to break this up into two separate terms. I'm going to put this thing over delta x, and I'm going to put that thing over delta x. I think what I did next was I said I have the limit of the difference of two terms. I'm going to compute the limits separately. So limit of the first minus limit of the second And what did I do in the proof before? I think I looked here and said, you know what? With respect to delta x, cosine of x is a constant. So what I have is the limit of a constant times this function. I can rewrite that as the constant times the limit of the function Ooh, that looks good. That looks very good. I'm going to do the same thing here. With respect to delta x, sine of x is a constant. So I have the constant sine of x times this function. I'm just going to bring the sine of x out in front of the limit sign. And I like this. I like this a lot because I know what this limit is. As delta x goes to 0, sine of delta x over delta x is 1. And I know what this limit is. As delta x goes to 0, cosine of delta x minus 1 over delta x goes to 0. So I have cosine of x times 0 minus sine of x times 1. And that's going to be negative sine of x. Congratulations, ladies and gentlemen, you have just produced the derivative of cosine of x. And let me make an appeal to you. You're taking notes, that's good. The two proofs that we just did, the derivative of sine of x and the derivative of cosine of x, when you get done with this video and when you get done taking notes, see if you can reproduce the proofs for the derivatives of sine of x and cosine of x. If you get stuck, go back to the notes and just see where you're getting stuck. But I think it's well within our grasp to be able to prove both of those theorems given the special limits that we derived prior to that. If we get stuck, it's okay. Try it again later on and see if you can make your way all the way through the proofs. Now, are we done yet? No. We got a bit more. Oh, things are just getting good right now. Yeah, I guess that showed up. Now, most of you learned the product rule as first times derivative of the second plus second times derivative of the first. Same thing. Here I just have derivative of the first times the second plus derivative of the second times the first. Appearance-wise, it's a little bit different than what you're accustomed to seeing, but completely equivalent. To do this proof, I'm just going to introduce an auxiliary function, h of x, which is the product of f and g. the derivative of f times g is the derivative of h of x. And by definition, the derivative of h of x is h evaluated at x plus delta x minus h evaluated at x all over delta x. And we're computing the limit as delta x goes to 0. And that is equal to the limit as delta x goes to 0 of, okay, in terms of f and g, what is h evaluated at x plus delta x? Don't we take x plus delta x and put it both of these places? So we have f of x plus delta x, g of x plus delta x, and then minus h of x, that's minus f of x, g of x, whole thing over delta x. Now, I might say here that there's a standard trick for doing this to make the proof easy. And here's that standard trick. I'm going to subtract a term . Well, I can't just do that. I can't just subtract something for no reason at all. So to atone for my sin, I'm going to add it right back. So I added this term, I subtracted this term, and let's not forget about this guy down here. I haven't written this term up here. I'll do that now. There. Now, why on earth was it advantageous for us to subtract this term and then add it back? Apparently, I want to group the first two terms, and I want to group the last two terms. So let's see. These first two terms have a common factor of g of x plus delta x. I'm going to factor that out. So I'll have f of x, whoops, come on, Pat. I'm going to have f of x plus delta x minus f of x times g of x plus delta x. I factored g of x plus delta x out of the first two terms. Now I got the last two terms, and the common factor here is f of x. I'm going to factor f of x out of these two terms. And then I guess I'll break this up into two limits. This thing over delta x plus that thing over delta x. So here's the limit of the first one, plus, whoops, guess I'm not ready for that yet, f of x times g of x plus delta x minus g of x all over delta x I have the limit of a sum of two functions. I can break that up into the sum of the two limits. So we'll have limit of the first and limit of the second. Yep, I like the way this is looking. Now, this first expression, I can look at this as g of x plus delta x times this whole thing. So I have the limit of a product here. This whole thing times g of x plus delta x. I can rewrite that as the product of the two limits. So limit of the first thing times limit of the second thing. And let's look at this expression. You know, with respect to delta x, f of x is a constant. I have f of x times this thing, that is a constant times this thing. Well, if I have the limit of a constant times a function, I can just move that constant out in front of the limit sign. So I'll take the f of x and put it out in front of the limit. And it's the limit of this thing. G of x plus delta x minus g of x all over delta x. Oh, this is looking so good. This is looking so good. What's that limit? Son of a gun, this is f prime of x. And this limit, remember, by our hypothesis, f of x and g of x are differentiable. And differentiable functions are always continuous. So this is a continuous function. So as delta x goes to 0, g of x plus delta x is going to go to g of x. And here's f of x. And this thing, do you recognize it? This thing, g prime of x. Whoops. So I have f prime of x, g of x, plus g prime of x, f of x. We just did the product rule. And I will make an appeal with you for this function also, or this proof also. Study the proof and then see if you can reproduce the proof without looking at the notes. If you get stuck, take a peek at the proof in your notes. But work on this a few times and see if you can work through it without looking at the notes. Now there's one more thing that I would like to do today, and that's the power rule. I'm not going to show you the standard proof. That's rather complicated. But I have a much simpler proof, and it's an induction proof. and I can't wait to show it to you. For right now, we're only going to show true for non-negative integers. This is our proposition. And here's what I'm going to do. I'm going to show that the proposition is true for n equal 0 and n equal 1. So, let's see, this is our f of x. F of x equals 1. So the derivative of that is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x well, that's the limit of 0, which is 0. Now, can I write it in terms of x to a power? Let's see. 0 times x to the negative 1 0 times x to the 0 minus 1, which is n times x to the n minus 1, where n is 0. So it works for n equals 0. Okay. Let's show that our proposition also works for n equal 1. This is our f of x. F of x equals x is our f of x. So the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And that's equal to limit as delta x goes to 0 of delta x over delta x. And that's the limit as delta x goes to 0 of 1. And the limit of a constant is 1. Now, can I write this in terms of n times x to the n minus 1? Let's see. Here's n. And if n is 1, then x to the n minus 1 is x to the 0. Yeah, okay. So when n is 1, here's what I just showed. Derivative of x to the n is n times x to the n minus 1. So I've shown this true for for n equals 0 and for n equal 1. Now I want to do the general case. Assume that my proposition is true for some non-negative integer k, and show that that means that it's true for k plus 1. So that is, assume that the derivative of x to the k is equal to k times x to the k minus 1 and show that the derivative of x to the k plus 1 is equal to k plus 1 times x to the k. Now, in an induction proof, we have the right to assume that our induction hypothesis is true. And there it is. Here's our induction hypothesis. We have the right to assume that that's true. And the proof gets really, really simple from this point on. Now remember what it is that we have to show. We have to show that the derivative of x to the k plus 1 is equal to k plus 1 times x to the k. Well, son of a gun, this is nothing but a product. And we're going to get the derivative of the first times the second plus derivative of the second times the first. Now, I know that derivative of x to the k is kx to the k minus 1 by the induction hypothesis. And this whole thing is true by the product rule. Derivative of the first times the second plus derivative of the second times the first. And now we'll just group everything together. So let's see. X times x to the k minus 1 is just x to the k. Kx to the k plus x to the k. Okay, I'll just factor x to the k out of each of these terms. I factor x to the k out of this term, I have k. I factor x to the k out of that term, I have 1. Oh my goodness, that's exactly what I was supposed to get. So here's what we just showed. This is what we just showed. Beautiful, beautiful. This is not the proof of the power rule that you'll see in any book, but it's a nice proof because we get to use induction, and typically we don't have a lot of exercises using induction that deal with things other than sums, so this is a nice induction exercise. Well, I think we're going to stop our lecture for today, but we made quite a bit of progress. We computed derivatives of sines and cosines, and before we could do that, we proved two well-known limits from calculus and real analysis. We've done the power rule and the product rule. So we had a very fruitful day. Everybody, please stay safe. Please exercise soundness of mind in everything that you do. And don't worry about what we can't do right now. Just worry about what we can do. Let's do what we can do. Study hard, learn this material. Some of these proofs we should be able to reproduce once we've seen them, so work on that too. And until next time, stay healthy and stay safe.